So today we are very happy to have Matjaž Konvalinka. He was a grad student of Igor Pak at MIT. Now he's a professor at the University of Ljubljana in Slovenia. But today he's actually in Sweden at the Mittag Leffler Institute. So this is becoming a very international virtual colloquium. So he works on enumerative and algebraic combinatorics, and he recently won the Robbins Prize along with Roger Behrendt and Niels Fischer for a paper on alternating sign matrices, where they proved that 30-year-old conjecture about the enumeration of a certain symmetry class of alternating sign matrices, that it was the only open case that had been open for a long time. And today he's going to talk about something related to that. So he'll tell us about the first bijective proof of the famous alternating sign matrix theorem. So go ahead.
Thank you very much, Sergi, for inviting me and for the introduction. So it's a bit unusual to be giving a talk like this. So yes, please, if you do have a question, do interrupt me. I don't see your faces. I don't know if you're nodding or, so please let me know. So first of all, so this is, again, a joint paper with Ilse Fischer from the University of Vienna. Yes, so it is a bijective proof of the ASM theorem. So as you might know, it's been an open problem for a very long time. But don't expect, a simple bijective proof. So if that's what you're here for, you should leave now, and that's it. So let me start with this definition. So what is an alternating sign matrix? It's a square matrix with entries 0, 1, and -1, so that in each row and in each column, the non-zero entries alternate and they sum up to 1. So an example of an ASM would be a permutation matrix, but obviously we also have many other examples. So here on the left, you can see the smallest ASM that is not a permutation matrix. Here is a 6x6 ASM, and well, there are many more alternating sign matrices than permutations. So this is the counting sequence, 1, 1, 2, 7, 42, etc. And well, this is this theorem, this famous ASM enumeration theorem, which states that the number of n by n ASMs is equal to this beautiful product formula. So you have quotient of two products of n factorials. Okay? And actually, you can be a bit more specific than that. So if you think about the first row of an ASM, well, there cannot be any -1s in the first row. Why is that? Because then the corresponding column would start with a -1, and that would not work because one of the requirements is that the sum is 1. So it has to start with a 1 and then a -1 and then a 1 again and so on. So it means that there's going to be exactly one non-zero value in the first row, and that's going to be a 1. And if you say that it's in position 1i, well, then you have this refined count of alternating sign matrices with of size n times n, and with 1 in position 1i. And this is the formula. So as you can see, the same as before, but now it's multiplied by another fraction. Okay, so this is very famous. A little history. So ASMs were introduced by Robbins and Rumsey in the early 1980s when they were studying their lambda determinant. And then they formed these conjectures about enumeration together with Mills. And Stanley pointed out that the same product formula had shortly before also appeared in Andrus's paper on the weak Macdonald conjecture. So you have the same formula for two very different objects. So in that paper, Andrus introduced descending plane partitions. I will define them a little later. And he proved that the number of descending plane partitions with parts at most n is enumerated by this formula. Okay. Then, a little later, Robbins introduced a new operation on plane partitions called complementation. And then he tried to count totally symmetric self-complementary plane partitions. I will not define that, but well, it's a pretty reasonable definition that fit inside a 2n by 2n by 2n box. And he again conjectured that they're counted by the same formula. So you had these three objects that seemed totally unrelated, but they seemed to be counted by the same counting sequence. So famously, this ASM theorem was first proved by Dora and Zeilberger in the early 1990s. So as you can see, this was a pretty long proof, 84 pages, also a pretty complicated proof. So the results in the paper are organized as a tree. So you have this lemma 1, which is the main statement, and this lemma 1 follows from sub-lemmas 1.1 and 1.2, and then you have sub-sub-lemmas and sub-sub-sub-lemmas and so on and so on. And the referee kept finding mistakes. So in the end, he decided to pre-referee the paper, and he found 88 people who then, pre-refereed this paper, found all the mistakes, and then the paper was accepted. Okay, and then very shortly afterwards, Greg Kupperberg found a much shorter proof based on this observation that ASMs are equivalent to the 6-vertex model with wall boundary conditions. This was something that had been studied before by physicists, and he was able to adapt the techniques developed by physicists to study this model, and he found a very elegant proof of the ASM theorem. Okay, then those totally symmetric self-complementary plane partitions were enumerated in '94 by Andrews. And then a lot of work was done in ASMs. So for example, the study of symmetry classes. So for example, you want alternating sign matrices, which are symmetric with respect to some symmetry of the square. And also very interestingly, very recently, Arvind Iyer, Roger Barrett, and Ilse Fischer introduced another object that they call alternating sign triangles, which again have the same enumerative formula as ASMs. So I already mentioned the two proofs by Zeilberger and Kupperberg, and Ilse Fischer developed her own proof in the past 15 years or so. So her proof was really very different. So she's using something that she calls an operator formula for monotone triangles. And I'll be talking about this mostly, but no bijections were found. So with, well, one notable exception, basically all the bijections they could find were trivial, like the one I'm going to show you very shortly. Otherwise, things were they just seemed impossible to prove with a bijection. And of course, well, if you're a combinatorialist, then you appreciate bijective proofs the most. So here is a quote by Stanley. So that's his opinion about ASMs. Christian Krautenthaler also said something along these lines. And I would say that, well, the best answer as to what all those objects have in common is that monotone triangles are connected to all of them. So they're kind of like the connection between all these objects. Okay, so let's start with another definition. So what is a Geltand-Tsetin pattern? So a GT pattern for short is a triangular array of integers, positive, negative integers, doesn't matter, so that the following is true. So if you look at 3 elements like that, so for example, A31, A21, and A32, then either this sequence of those 3 numbers is weakly increasing or it's strictly decreasing. So these are the 2 options. Okay, so you could say that the classical Geltand-Tsetin patterns are the ones where this is satisfied, this weak increases everywhere. But, well, this is a more general setting. You also allow decreases, but then they have to be strict. Okay, and well, importantly, such an array has a sign. So it's either a positive pattern or a negative pattern. And the rule is that you take -1 to the number of descents. So whenever you have a descent, you count that as a minus. And then, well, you count all such minuses and you get the sign. Okay, and this is well known. So what is the number of GT patterns? And when I say number, I mean signed enumeration. So you take the number of positive ones minus the number of negative ones. And the rule is that you get this nice product formula. So if you look at GT patterns with bottom row K1 through Kn, this is the formula that you get. So this is an example. If you look at bottom row 1, 2, 3, you have 8 options. Well, that's what the formula predicts. And as you can see, you indeed have exactly 8 options. Okay, so these are the GT patterns. So any questions so far? What about monotone triangles? So a monotone triangle is also a triangular pattern of integers. And the definition is a bit complicated, so I'm not going to tell you the exact definition. I'll just tell you the special case when the bottom row is strictly increasing. So in that case, a monotone triangle is simply a GT pattern so that all the rows are strictly increasing. Right? If you look at bottom row 1, 2, 3, well, not all GT patterns are monotone triangles. This one is not, with 2 2s in the second row, right? Because it's not a strict increase. So you have 7 of them. Okay, and here comes this one of the trivial bijections. So a monotone triangle is in an easy bijective correspondence with an alternating sign matrix. More precisely, a monotone triangle with bottom row 1 through n is in a bijective correspondence with an ASM of size n by n. And how does this work? Well, we start with an ASM, and then you take the matrix of partial column sums. So, for example, if I take the sum of the first 3 rows, I will get 1, 0, 0, 1, 0, 1, as you can see here, right? So it's easy to see that now you just get zeros and ones, right? Minus 1 disappear. All the partial sums are 0 or 1. And also it's easy to see that in every row, you have exactly one more than before. So you start with a 1 in the first row, then you have 2 1s, 3 1s, and so on. And then you can record the positions of those 1s. And you get a triangle. And of course, you do have strict increases. And also this GT rule, you know, of weak increases along diagonals is also easy to see. Okay. So can we also do a signed enumeration of monotone triangles? So I just gave you, you know, the sum of the positive monotone triangles. You can also define monotone triangles with a different bottom row where it's not strictly increasing. And then you can also get a negative sign, like with GT patterns. And well, for example, if the bottom row is K1, K2, then the number of monotone triangles is K2 minus K1 plus 1. Okay. Why? Well, if K2 is bigger than K1, then you can put any number between K1 and K2 there, and this is their number. And this also works when K1 is bigger than K2. Okay, then there's going to be negative monotone triangles, and well, that's exactly the number that you get. What about if the bottom row is K1, K2, K3? Well, you might hope for a simple formula, but as you can see, it's not exactly simple. It does not factor. It is still a polynomial, right? Still a polynomial of degree 3, like before for GT of K1, K2, K3, but it's not as nice anymore. Okay, and this is this beautiful, important theorem by Ilse Fischer. She calls it the operator formula, which tells you that monotone triangles and GT patterns are connected in some way. Okay, so EI is the operator that replaces the variable ki by ki plus 1. And then what do? You take that simple polynomial for GT patterns, and for every choice of I less than j, right, there's a lot of choices, and choose 2, you pick either EI, which means you're going to increase ki by 1, or you pick EJ to the minus 1, so that means you're going to decrease kj by 1, or you're going to do both, but with a minus sign. Okay, an example. So how do you compute MT of K1, K2? Using this formula, you take this simple formula for GT, K1, K2, and then, well, now you just have one choice, right? 2 choose 2. So either you increase k1 by 1, this is what you do in this first term, or you decrease k2 by 1, or you do both. And when you do all the simplifications, you get k2 minus k1 plus 1. And of course, you can try that with k1, k2, k3 as well, right? But there's going to be a lot, it's going to be a lot more work, because there you have, well, 3 choose 2 choices for I and j, so that's 3 of them, and for each you have 3 choices for which of those e's you're going to take. So you have 27 operators acting on this, and well, once you do that and compute, you're going to get that expression that I had before. So I like to think of this as sort of inclusion-exclusion, right? So you would want to take all Geltand-Tsetin patterns, and then you would want to subtract the ones when there's an equality between 2 consecutive numbers in a row, but then you subtracted some of them twice, so you have to add that back. Right? You would kind of want to do inclusion-exclusion, but you can't really, because there's no way to count the number of GT patterns with equal signs somewhere, right? So this is not inclusion-exclusion. It just kind of reminds me of that, right, with this minus signs. Okay, so and now I'm going to tell you about this project with Ilse Fischer. So the goal is to convert her proof of this operator formula into a bijection, and then to use this bijection to construct a bijection which proves the ASM enumeration formula. Okay, so what does that even mean, to biject, to have a bijection that proves this formula? Well, I'm going to tell all of that in a bit. So here is a slide that shows you, our first steps toward a bijective proof. So we kind of understood what we had to do. So we delved deep into, her proof, and we realized we had some 6 tuples of objects, and then we wanted to do some sign reversing involution that would cancel some of those objects, and then another sign reversing involution, and so on and so on. And what happened was that, we kind of could do it, but what we got was completely unreadable, even to us immediately after writing it. So it was obvious that we needed a slightly different approach. We kind of had to break down this complicated proof into smaller bits. And well, we did not know how to do that immediately. So it turns out that the concepts one should use are signed sets and signed bijections. Okay, so we call signed bijections sijections for short. So what is a signed set? Well, it's very simple. You've all seen this probably. So you have a pair of finite sets. So I'm going to assume everything is finite, and they should be disjoint. So this is it, right? Some positive elements and some negative elements. Another way to say that is that you have a finite set and a sign function. So a function that tells you which elements are positive and which are negative. Okay, what is the size of a signed set, right? That's the same as signed enumeration I talked about before. You take the size of the positive part and subtract the size of the negative part. Okay, also the opposite of a signed set is something very natural, right? Just switch the 2 sets. There are many other things you can do, like Cartesian product, right? So these are pairs. Which pairs are positive? Either both components are positive or both are negative. And otherwise, you have a negative pair. This was also very important, disjoint union, right? So you have 2 signed sets. This is also a signed set, right? 0, and then the empty set is the negative part. So this product is a signed set, and this is a signed set, and they're disjoint, so you can just take their union, and you're going to get a signed set which has the right number of elements. And actually, what was really important was the following definition, right? So you all know that if you have a family of sets, then you can take the disjoint union of those sets, right? And usually it will be indexed by another set. So it was very important that we realize that with signed sets, you have something similar. So you have a family of signed sets, which are indexed with another sign set. And you can take the disjoint union of those sign sets over a sign set, right? So what does that mean? It just means, well, if an element in the indexing set is negative, there's going to be a minus. Okay, so it's very simple, but as I said, this really was a crucial observation. Okay, and well, most of the usual properties of Cartesian products and disjoint unions extend to sign sets, right? So like associativity and distributivity, commutativity, you can prove all of those very easily. Okay, I said we had to break down the proof into smaller chunks. So signed sets are built up of these building blocks, which are signed intervals. So everything that we're going to do will somehow involve signed intervals. So what is that? A signed interval means that you have a and b, which are integers, and it doesn't matter which one is bigger. You have this signed interval defined. How is it defined? Well, if a is less than or equal to b, then you just take the usual interval and all the elements are positive. And if a is bigger than b, then you take the interval from b plus 1 to a minus 1, and all the elements are negative. Okay. Why is that a good idea? Well, if you compute the size of this sign set, you're going to see that it's always equal to b minus a plus 1, right? No matter what a and b are. Also, well, it's easy to see the following, right? If I take a minus in front of a signed interval, it means that I switch a and b, but also I add 1 to b and subtract 1 from a. Okay, and the sign sets we consider are usually constructed from signed intervals using Cartesian products, right? So you get signed boxes and disjoint unions. And as an example, well, a GT, this sign set of GT patterns can be defined using disjoint unions and Cartesian products, right? So it's a recursive definition. So GT pattern, well, you have the bottom row, and then you choose LIs in those sign intervals, right? So it can happen that K1 is bigger than K2, but that means there's going to be a minus here, right? So here, I don't have to specify the signs. The signs are already hidden here in this sign box. Okay, what about signed bijections or sijections? What are those? Well, this is our working definition. So a sijection from S to T is an involution on this disjoint union. So you take all the elements in S, disjoint union with all the elements in T, right? It should be disjoint union because S and T can have elements in common. And this is the property. So it has to be an involution which satisfies this property. What is this saying? It's saying that an element of S plus should either go to S minus, right? So it's a sign reversing involution within S, or it should go to T plus. So it's a sign preserving map to D. Okay, and vice versa for T minus, right? And well, this also follows that S minus goes to S plus or T minus and so on. Okay, so another way to think of this is as a collection of a sign reversing involution on S, on some subset of S, a sign reversing involution on some subset of T, and a sign preserving matching between the remaining elements of S and T. So here's a picture to have in mind. So you have sign set S, sign set T. Some elements of S cancel. This is this yellow part. Some elements of T cancel, right? There's an involution between them. This is this green part here. And then the remaining elements of S plus are matched with the remaining elements of T plus, and same for S minus and T minus. Okay, and well, if you have a sijection, then the sizes of the two sign sets are the same, right? This is obvious. This yellow part cancels, this green part cancels. Those two are also equal, so you get equality. So this is a way to prove that two signed enumerations are equal. And of course, if S minus and T minus are both empty, well, then there's no cancellations. This is just a bijection. Okay, and well, as I said, we need to construct more complicated things from simpler things. So we can construct Cartesian products, disjoint unions of sijections. I'm not going to write the precise statement. And you can also compose two sijections. So this is equivalent to the very famous Garcia-Milne involution principle. So how do you compose two sijections? So you want a sijection from S to U. There are some cancellations here, some cancellations here. You keep those. And then, well, if you start with an element in S plus, it maps to an element in T plus via this first sijection. And then the second sijection can either map it to U plus, in which you've found the matching, right? You've sent something from S plus to something in U plus, or it sends you to T minus. And then once in your T minus, you use the first sijection again, which can either take you to S minus, in which case you found matching between something from S plus and something in S minus, or it takes you back to T plus. Okay, and you continue in this way, so you're going to be stuck in T for a while, but not forever because it's a finite set, right? So in the end, you have to be thrown out somewhere, and this gives you the composition. Okay, and here, well, I told you that the signed intervals are the building blocks of signed sets. And this sijection alpha, a very simple sijection, is the building block for all other sijections we're going to consider. So it says that there's a sijection from the signed interval from A to C to this disjoint union, A to B, and then B plus C to C. This is the same as this second disjoint union, right? I just used that property of what the opposite of a signed interval is. So an example, A and C are 1 and 8, B is 5, then yes, of course, this interval and those two intervals are in a sijection. It's actually a bijection, right? There are no cancellations. But also if you take this 1 to 5, these are all elements 1 through 5. These are all the elements 1 through 8. And those are all elements from 6 to 8, right? Strictly between 5 and 9, but they are negative. So what do? You match those 6, 7, and 8 from here, and what remains are 1 through 5. So you see, it's a sijection, and similar for all other instances of how A, B, and C are ordered. So this is the building block, very simple. Also note, I call this a problem, not in the sense of it's an open problem. So if you attended FIPSAC in Ljubljana and attended Andrej Bauer's talk about what is an explicit bijection, he talked a lot about how mathematicians say, there exists a bijection between those two, but then a few lines later, they use that bijection, right? If you just say it exists, that's all, right? And if you want to use it, then you should not call that a theorem, you should call that a problem, and then there's a construction instead of a proof. So this is, for example, how Voivodsky did it in some papers of his. Well, so we're following that as well. So this is a problem, and then this is a construction that shows it. Okay, and then, well, you can use this building block, this alpha, to construct other sijections. So this is an example. So you have a signed box, and you can construct a sijection from this signed box to this disjoint union of signed boxes. Right? You see, well, this is just one signed box of dimension n-1. This is actually a signed box of a dimension n, so one more. And also there are more of them, right? There are 2 to the n-1 of them, right? Each of those SIs has 2 elements, one positive and one negative. So you might wonder, why do you want to have a bigger signed box and lots of them? But you're going to see soon. So how do you prove this? Well, for n equals 2, this is just the map alpha that I described. So this is the base of induction, and then you can use induction, right? So you want sijection from this Cartesian product, but you already know the sijection from the Cartesian product of the last n-2 of them. So you use induction. And then, well, all L2 is in S2, so it is either equal to A2 or it is B2 plus 1. So you split this into 2 products. And then for each of those products, you use alpha on this first interval, but a different alpha, right? Your goal is for this second one to be equal to the first one in the next product, right? That's what the right-hand side is like. Okay, so here in the first one, the last one should be A2, and in the second one, the last one should be B2 plus 1. Okay, and then you just put this all together and you get a sijection. Okay, and once you have all this, so this is not the only one that we construct, but once you have all these sijections for signed boxes, you can move on to sijections for GT patterns. So you see you're kind of building up more complicated structures. So similar conditions here, right? You have two sequences of n-1 integers. You define this Si as a signed set with a positive and a negative integer. And then you have this sijection. Okay, how does that work? Well, remember, we just constructed beta from this to that. And then we can do a sijection from a disjoint union over those to a disjoint union over those. And then you can switch a little bit. You have two disjoint unions on the right. You can switch a little bit, and then you have disjoint union of GT patterns over this product. And this is by definition, right? Remember that recursive definition, just a GT pattern. So it's a very simple proof once you have the map beta. And you see now that does make sense, right? So the GT patterns are a bit bigger, right? They have one dimension more. But before, this was over all elements in a signed box. And now it's just over the, well, corners. So this is the kind of stuff we're doing. Okay, two more sijections for Geltand-Tsetin patterns. So if you have GT patterns with bottom row K1 through Kn, you can switch two consecutive numbers. You add one to the second one, you subtract one from the first one, and you get a minus sign. Okay, so again, not too hard. This is also useful. So you have two sequences, and AI plus 1 is 1 less than AI, and BI plus 1 is less than BI by 1. Then this disjoint union of GT patterns can be sijected to the empty set. And what's nice about these two problems is that both use induction, and, well, the induction step for problem 1 uses problem 2 and vice versa. So you can kind of construct them at the same time. Okay, more definitions. So what is an arrow row of order n? So, well, I have n arrows. Each can be either to the right or to the left or both. And if it's both, it's a negative. And what is the role of arrow rows? Well, they give me a deformation of this product that we keep seeing, right? This product where you have two consecutive numbers equal. For example, if I take k to be 4, what does that mean? Well, if there's an arrow pointing at k1, that means I'm going to increase k1 by 1. And if there's an arrow pointing toward k2, I will decrease it. Okay? And here again, arrow pointing here, so I increase. Arrow pointing here, I decrease. No arrow, so I leave it as it is. An arrow, so I decrease. Okay, so it's a certain deformation of this. And, well, this is a recursion, you can say, for monotone triangles. This is not too hard. So you have monotone triangles on the left, and then smaller monotone triangles on the right. And you can construct a sijection. And this is not too hard. This really means you have to find some sort of a sign reversing involution on the right-hand side and match the remaining elements. And this proves this. Okay. So I mentioned arrow rows. What about arrow patterns? Well, arrow patterns are something similar. So again, you have arrows. Now they're pointing down, but now you have more of them. So you have n choose 2 of them. And the role is that they give me a deformation of this final row, K1 through K4. How does that work? Well, let me show you here with K2. For K2, you look at the number of arrows that point at it from the right and subtract the number of arrows pointing at it from the left. So that's 2 minus 1, so K2 plus 1. is the appropriate deformation. And K3, 1 minus 0 plus 1. And K4, 2 arrows pointing at it, so minus 2. And finally, well, I can define shifted Geltand-Tsetin patterns, which is disjoint union over all arrow patterns of size n, and then GT patterns of this deformed bottom row. So what's the point of this? Well, remember the operator formula, right? You have GT patterns, but then for every element, every choice of I and j, right? Exactly, n choose 2 of them, right? It's exactly one element in that triangle. You either pick an arrow pointing to the left, which means that ki is increased by 1, or kj is decreased by 1, or you do both, but you have a minus sign. So you see, this right-hand side is precisely enumerated by this SGT. And this difficult part is to prove that SGT satisfies the same recursion as MT. So this is by far the most difficult problem in our first paper. So we have 2 papers in the series, and this first paper has this as, its crown achievement. So there's the same recursion as for monotone triangles. And now this really is difficult. You use all the sijections you constructed before in a clever way. So it is a complicated, like slightly more than 1 page, but lots of sijections from before used at different times. Okay. And once you have that, well, you can get this gamma map, which is a proof, a bijective proof, sijective proof, if you will, of the operator formula, right? And how does that work? Well, I told you about this easy recursion for monotone triangles. By induction, you already have a sijection between those 2, right? Because L is smaller. So we can take then the disjoint union of those sijections to get a sijection to here. And then you have this difficult sijection to SGT of K. And this gives you the required sijection. Okay, so for this second part, I'm going to be very brief. So we're not there yet, most definitely not, but I'm going to describe just a few crucial steps. So the next thing you should do is you want to prove rotation of monotone triangles. So you want to construct a sijection between monotone triangles with bottom row K1 through Kn, and plus or minus monotone triangles with rotated bottom row. So you shift K2 through Kn1 to the left, and you put K1 at the end, but you decrease by n. Okay, and this is actually the only time in this second paper where we use the sijection between monotone triangles and shifted Geltand-Tsetin patterns, right? So the idea is, well, it's enough to prove this sijection for SGT, right? Then you can just shift back to monotone triangles. And with GT patterns, remember you have that switch of consecutive ones. So you can just do the switches, consecutive switches, and you're going to get a rotation. Okay, that's not it, because things don't work out quite as easily. You still have stuff to prove, but that's the basic idea. So you need a few more sijections, a few more computations, and you get this rotation. Okay, and once you have this rotation, it's not too hard to prove this. Okay, so what is this? So ASM and J, remember that's precisely the object we're interested in. This is just a set of subsets of this size in this, living in this set. So these are both sets. So this is the usual Cartesian product, but then you take plus or minus that and the disjoint union. So this is some sign set on the left, and this is a set on the right. And you can use that rotation that I mentioned on the previous slide to construct this sijection. Again, not obvious, but not too hard. Okay, so how does that help you? Well, you can look at this. This is kind of like linear equalities for signed sets, right? Or sets in this case. And how do we solve linear equalities? How do we solve systems of linear equation? Well, with linear algebra. So what we need here is some bijective linear algebra. So let me show you a couple of examples of what I mean by that. So permutations are also a signed set, right? A classical signed set, right? Positive and negative permutations. And now if you have a family of signed sets, Pij, ij from 1 to m, you can define the determinant of that family of signed sets, right? Just take disjoint union over all permutations, and then here you take the Cartesian product, right? Note, there's no sign here. Why not? Because it's already hidden here in the sign set SM. Okay, and then this is the kind of construction you want. So if you have two such families and you construct the third family in a natural way, right? If you know some linear algebra, then this is a sign set, this is a sign set, and you want to construct a sijection between those two sign sets, right? So some cancellations on both sides, or maybe on one side, and a matching between the remaining elements, right? So it's a bit unusual because we're not used, at least I'm not used to thinking about linear algebra in this way, but the proof that you could write down as a polynomial identity on both sides really works well also in this setting. Another example, Cramer's rule, right? So if you have a system of equations, right, which is exactly what we have now, well, you're used to thinking about Cramer's rule as saying, well, if the determinant is non-zero, then you can compute xq, right? So I don't want to say anything about the determinant, but, well, it can be 0, right? It can be the empty, or rather not necessarily the empty sign set. It can be a sign set with size 0, right? But you still have, it's easy to see, you have a sijection between sign set times sign set to another sign set. So this is Cramer's rule, but this signed set version of that. Okay, so one last definition. So this is what I mentioned in the beginning. So Andrews defined descending plane partitions. So what is that? It's a filling of a shifted Young diagram with positive integers, with weakly decreasing rows, strictly decreasing columns, and then two more conditions. So the first part in every row should be greater than the length and less than or equal to the length of the previous row. Okay, and well, here's an example. So you see shifted Young diagram, weak decreases along rows, strict decreases along columns, and well, this 6 is bigger than the size of the first part. And this 5 is bigger than the size of the second part, and also less than or equal to the size of the previous part. So DPPN is the set of all DPPs with entries at most n, DPPNI, the subset with precisely I minus 1 occurrences of n. So this here, for example, would be in DPP 6(3). And well, by Geselviano lemma, we can express the number of DPPs with entries at most n, and also with exactly I minus 1 n's as a certain determinant. Okay, so remember, we found these linear equalities for the sets we're interested in. So what can we do with a system of linear equalities? We can use Cramer's rule, right? And we're going to get determinant of this matrix of coefficients times the set we're interested in maps to something. Okay, so well, what you have to do is you want to find a sijection from this determinant to something nice. And well, this is as nice as it can be. It's not too hard to find a sijection to DPP n minus 1, and on this right-hand side to this set. And as a result, you have a sijection between those two sets, right? But well, if you have a sijection between two sets, not sign sets, right? Those have no negative part. That means you have a bijection. So something goes from here. There are lots of sijections in between. It gets tossed around for a long time, but eventually it has to come out on the other side, right? It can't return because there are no negative elements here. And this is the bijection, right? It's a bijective proof of this equality between DPP and ASM. Why? Well, by induction, you can assume that that's true for n minus 1, And then if it's true for n minus 1, then it's also true for n. So it's a recursively bijective proof of that theorem. Okay, so it was very clear to us from the start that we wanted computer code for that, right? So we did not want just, we have a paper and yes, in principle it can be done. We wanted actual working code. We did Mathematica first, but then we realized that it's better to do this in Python. So like the end result is over 2,000 lines in Python. You can download it and test it, see what this bijection is giving you. For example, well, how fast is this? Well, if I'm checking this for n equals 4 and for all i's that are interesting, 2, 3, and 4, it takes about 12 minutes. So this is pretty reasonable. For n equals 5, it's 4 days. So don't go higher than that. But a student at our department, a master student, is going to do this for her master thesis. She's going to write a better code in OCaml. So hopefully better and faster and more useful code is coming at some point. Okay, so this is an example, right? So if I take n equals 4, I equals 2, this is this bijection that I get. I was staring at this for a while. I do not see any patterns or anything, but well, it is a bijective proof. Let me mention something here. You see this x, right? I didn't say that clearly enough, maybe, but there's this extra parameter in all of this that we're doing. This x arises pretty quickly, and you carry it out. So for different x, you're going to get different bijections. But well, each of them works. So future work. Well, now that this is broken up into kind of smaller pieces, you might want to, well, simplify some of those pieces, right? So that's definitely what we would like to see done, right? To gradually simplify this proof. So of course, everybody's welcome to join and try to simplify part of this to make it, into a human, into a proof doable by humans as well, not just by Python. Okay, that's also a goal, right? That was one of the reasons why we were doing the coding as well. Can we see any patterns once we have this final bijection? We haven't seen any, but well, again, we plan to keep looking. And we also plan to, at some point, use similar techniques to also find bijections with these other two objects that we know are enumerated by the same formula. Okay, so if you want to read more about this, both papers in the series are on the archive. And thank you for your attention.
Okay, thank you. If you want to unmute yourself to clap. Okay, so if anybody have questions, you can unmute yourself and ask a question. If you don't have a microphone, you can also ask in the chat box. Maybe while people are thinking, I have a question, I guess two questions. So one is, if you have any estimate on the running time of the bijection. I mean,
no. So as you know, I mean, whenever you have this Garcia-Milne or involution principle or anything like this, things are pretty unpredictable, right? They're going to be traveling inside for an unspecified amount of time. So I would think that, I mean, you could possibly prove that it's bad, so, exponential or whatever. I'm not sure if you want to do that, but you're welcome to try. So it's definitely the case that for some elements, it's really fast. And then for some, it takes a really long time. So when I said 4 days, some of them are extremely quick, right? Like 0.002 seconds. But then every now and then, one comes that needs 5 minutes. So the running time is definitely bad, but that's to be expected.
Oh, there's a question in the chat box. Can you see it directly, or do you want me to read it?
There's so much here. Oh, the hydral symmetries, if they translate to anything nice. I don't think so. So this map is nice in the sense that, you know, it keeps track of the position of the one in the first row. But I think that everything else is going to be lost. So a number of minus ones, any kind of symmetry. I mean, you're welcome to check, right? You can download the code and try it, but I think everything is lost.
Okay. Anyone else wants to ask a question?
Yeah. So, Matjaž, so with this sijection technology, do you have other problems that need bijective proofs that you want to aim at? Maybe that use determinants.
So,
matrices?
I mean, yeah, that's a good question. So, I mean, one aim was to, you know, kind of think about how streamlined can you make this finding of bijective proofs, right? So, can you do it, you know, more or less automatically or something? So, I would love it if other people tried with, you know, their own favorite problems. We kind of dealt with this ASM problem simply because, you know, it's a very famous, very well-known problem, and we care about it personally. But I think it should work for other instances as well, right? So whenever you have something really complicated, yes, you should break it up. How should you break it up? You should break it up using this sijections, sign sets. You should build it from smaller building blocks. Yeah, so I do think that this technique is more widely applicable, but no, we have not tried it on any other problem.
Thank you.
Hello, this is
Hi.
Seth Chaikin.
Hi.
Yeah, I have a question. It's really cool, and I like the list of properties that you gave us about sijections. So I'm curious about. Could you elaborate on the relationship between sijections and the Garcia-Milne, involution principle?
Yeah.
So in particular, is the Garcia-Milne principle a special case of a sijection?
I would kind of say it's equivalent. So Garcia-Milne is equivalent to the statement composition of sijections can be done and is the sijection. I would say that this would roughly describe it. So, I mean, it's very likely that other people have noticed this before, but I never thought of Garcia-Milne in this way. So for us, yeah, this was the key moment when we noticed that, oh, we can compose those, oh, and that's just Garcia-Milne.
Okay,
so
thanks.
So also maybe I should mention here, so a guy in my department who, you know, likes category theory and logic and all that, he said, oh, this is, you know, something from category theory. So you have, wait, what was it? Traced monoidal category or something. And so we talked a little bit about this, and he said, oh, yes, so this is a special case of that. But nobody ever does this as an example. I don't know why, you know, because sign sets are a really natural thing. And then I said, oh, and by the way, what we really needed was, you know, this disjoint union over sign sets. And he said, oh, well, I don't see, you know, a categorical way to say that. So I think it is, it is a special case of something more general in category theory, but sign sets are special in this way, at least as far as I understand it.
Huh. It would seem that disjoint union can be described categorically.
So yeah, so co-product something.
Yeah.
Yes, but so when I said this, well, can you have now a sijection, right? So a sijection between those two, like for a general category, and then he was like, no, but I did not think about it at all.
Yeah. I guess the first step would be to what would the morphisms be?
Actually, yeah, I think that these are the morphisms. You know, it's like kind of like, you know, if you take category, you know, finite sets, and bijections are the morphisms. So if you just take a morphism in the sense that, you know, a map is for a regular set, then you have no composition. So you really should have sijections. So bijections, this sign bijections as your morphism.
Mm-hmm. Any other questions? How many referees do you think it will take for this one compared to the?
Okay, so I think it's a very readable paper. So I think that, you know, standard 2 referees will be enough. Yeah.
Okay, so if there are no more questions, let's thank Matjaž.